we realized that you're having to have the MATLAB grader run something that calculates a 128 cubed image was going to be maybe make a timeout. You'll have to compute that 128 cube image to get the results that you need, but you will not turn in the 128 cubed image, the calculator of that 128 cubed image, but rather a 16 cubed image. And Mike will explain what the story is on that.
Yeah, so basically the MATLAB grader will time out if we actually run a 128 by 128 by 128 image. So the MATLAB grader will actually just run a 16 by 16 by 16 image. And in the MATLAB grader, you will see that there is a section under code to call my function. We will actually give you like an example of how the 16 by 16 by 16 image will look like. And you can run your code based off of that so that you don't have to wait like 5 minutes for each iteration of your code.
Okay. So with the MATLAB grader for this string, you'll have this example input that you should be able to try your results on, your method on. Questions on that? Okay, we're coming up to the end of the course. The final exam will be similar, hopefully with way fewer errors than the midterm. It will be, short answer on Sakai. I have put on Sakai the final exam of this course from 2020 in actually two files. One, the raw exam, and the other, the same exam but with answers, correct answers. So you can check what when you study, check the answers. On the final will cover the whole course. It will be a bit weighted towards the material that has not been examined upon. That is to say, we stopped in the middle of the multi-scale locality section. Basically, we talked about splines, but didn't work out exactly what splines were. That was where the boundary was. And so from then on, that all the rest of the multi-scale and locality section, the interpolation section, the geometric transformation section, and this ridges section that we're going to do today will be rather more weighted than the earlier section. I will go back to the midterm and find questions that people seem to have trouble trouble getting correct, and try to have questions in those areas. Anyhow, because there's no homework on the ridges stuff and the quaternions stuff is not fully, you certainly have a homework on it, that's what assignment 8 is, but probably valuable to you to have some extra practice questions in those two areas. And so I'm putting some extra example questions in those two areas also in the resources section of Sakai. The finals there now, I'll get the extra questions on ideally by the end of today. The exam will be available on the morning of Saturday, April 30th. I think that's the right date. And you will have from then till 11 o'clock on May 3rd. The course nominal final period is 8 to 11 on May 3rd, and so the due time is the same time as the end of the nominal final exam period. Any questions on that? I want to emphasize that I will be having office hours. I will be open for appointments. And if there's demand, I can put in extra specific office hours. And I encourage you, if you are having any feeling, well, if you've had difficulties in any area or have questions, to come to those as you study for the final. The rest of the class, as this says, the rest of the course consists of only 3 lectures. Today will be the final lecture on new substance. I'll do a summary lecture for the whole course with emphasis on the last half next time. And obviously take questions as I'm presenting that. But the final class, which is a week from today, will be dedicated to your questions on the course material. Any questions, suggestions? Okay. So we have just completed the material on geometric transformations. We've seen lots of different kinds of transformations. We've seen rotations and translations and so on. We've seen deformations. We realize that what's going on when you want to transform an image according to one of these geometric transformations is that you're applying a transformation strictly to the positional variables, x, y, z, if you're in 3 dimensions. And if you have a discrete image with voxels, let's say in 3D, you want the result, the transformed image, I prime, transformed from I, at its pixels. And therefore, what you do, you've seen this in assignment 7, you apply the inverse of the transform from the target place J to a place in the original image, J double prime, and then that gives you a position in the image, and you have to interpolate the intensity there and put it in pixel J in the result. So since you're doing G inverse, and that was exemplified in the homework assignment where the transformation was translation by delta x, but the inverse was translation by minus delta x, and that was the one that's the G inverse that you applied, right? And if you happen to want to have a series of transformations, G1 followed with the result having G2 applied on it, I remind you that since you're going to need the inverse of G inverse is G1 inverse, G2 inverse. That is to say, you apply the second thing's inverse first, and then the first thing's inverse. And the example here, if you're rotating about the rotation matrices or the quaternions that we talked about are all rotations about 0, about the position 0. And if you want to rotate around some other place, then you need to have a translation operation, and then a rotation, and then quite possibly a translation back. And that would be a G1 followed by a G2 followed by a G3. and then you'd need to apply G3 inverse, then G2 inverse, then G1 inverse to get the final result. Is that clear? Okay, this is the end of the geometric transformation section. Let's see if I can bring up this one. Okay, so this is the section on height ridges. You'll see that in a little while that there are multiple kinds of ridges definitions, and they're not equivalent. We're only going to focus on one of them. If I have time, I'll talk about one other than the one we're going to talk about. But the one we're going to talk about is called height ridges, and it's particularly well understood definition. And so we're talking about a height ridge in a function of position. So I have here the table with XY coordinates in it, and I have this piece of clay, which is the height above the table, is understood in this example to be h of x. X is in the table, h is the value of the function, right? And there's a ridge here in this height. Realize, though, that the ridge is not on the clay. The ridge is on the table. It's a locus of positions in xy above which you have this height property, this ridge property in height. Okay? Any understand that? It's easy to think that the ridge is up there on the function. It's really down there on the table. Okay, an example that we've seen already, if you take the gradient magnitude of an image, and you're going to do that, of course, with a Gaussian derivative. We always take derivatives via derivatives of Gaussians. You'll get edge strength. If you have this image, that is this blue thing, that is, say, more intense here, less intense here, then the gradient magnitude will be particularly high along the edge of that region. And I put these little markers of cross-section to remind you that it's not just high here and zero everywhere else, but it rises to high and falls. And so you get this ridge effect along the edge. And what we're trying to figure out is where's that ridge? That's going to be where we compute the edge to be. Questions? Okay. So this is a slide set that I swear I changed this. I brought up the wrong file. But anyway, you're responsible for up to a particular place, but there's more slides in this set that I may talk about, but you're not responsible for. Okay, so we're talking about ridges, and here's an example of an image of edge strength of gradient magnitude. This is not I. This is magnitude of grad I. And what we're trying to do is find this curve, the curve that in xy that corresponds to this ridge. You're here in North Carolina. You understand ridges. The wonderful Blue Ridge Parkway is on one, right? And very close to it anyway. And I have lectured in the Netherlands, and it's harder to tell them about ridges because they don't have them. big flat country. Or if you're from eastern North Carolina, maybe you're in trouble with ridges. Anyway, but that's the kind of ridges we're talking about. And I have this example here that I'm going to be talking to. We'll see later that we'll be able to get ridges in three-dimensional images, three variables, or actually m variables. And we'll also see that our good old friend, the barness or bar strength that we looked at will be understood as a height ridge as well. There is a good deal of writing on height ridges. One of them is by David Eberly, who was a graduate student here in this university, and there's a lot of writing by Professor James Damon, now emeritus professor in the math department, on that, if you want to read further. Okay, so the first thing we have to get into your head is the notion of dimension. It's easily misunderstood. The idea is that any curve or any locus in space has at any given position a tangent plane or a tangent curve, and it has a tangent which is flat. And so in the case of this this function here, we have at some place on this here, let's say, we have a flat tangent plane. Okay? If we have a space curve at a point here, we have a tangent line. And the idea is that the dimension of the locus that we're talking about is essentially the number of degrees of freedom as you walk along that thing, which is the same as the number of degrees of freedom as you walk along that tangent. And so a curve in 3D has a line, and you have only 1 degree of freedom. Plus, positive or negative, you can walk forward or backwards along the line. That's all you can do to stay on the line. And so a curve in 3D is one-dimensional. The ambient space, the space in which it lives, is three-dimensional, but the curve is one-dimensional. And you have to get that into your head. Likewise, a curve on the surface, okay, is still one-dimensional, right? It's now ambient space is 2 dimensions, but it's still a line that is tangent to it, and a line has 1 degree of freedom. Okay, so a curve in 97 dimensions is still one-dimensional, right? And so this idea of the dimension of a locus is a property of the locus, and it's the number of degrees of freedom in the tangent locus, the flat locus tangent at any point. So if you're talking about a surface, the tangent is a plane, and a plane has 2 degrees of freedom, right? You can take 2 directions in that plane, and say any other direction is specified by how much of this and how much of that dimension. So you have 2 degrees of freedom. So a plane is 2-dimensional, and it's 2-dimensional if it lives in 3 space. It's 2-dimensional if it lives in 15 space. It's still 2-dimensional, right? Get the idea? Good. So, okay. I meant for this slide to be up before, but that's exactly what I said before. Okay. So now we're going to be trying to find ridges of some dimension in functions h that are of typically higher dimension. Could be the same dimension. Special case. And so in our example here, grad I is a function of two variables, x, y. The ridge is going to be a curve, which is one-dimensional. So we're trying to find a one-dimensional ridge in a function of two variables. Okay? Later, when we try to find the edges of regions, let's say a kidney in a medical image, you have high intensity in the kidney, low intensity outside. The gradient magnitude will be, this is a function of 3 dimensions, and we'll be interested in finding 2-dimensional ridges, which are the surface of the edge of that kidney in 3 dimensions. In other situations, we might be interested in finding 1-dimensional ridges in 3 dimensions. Okay, so this is what we're doing. And for our example, we're talking about h of x where x underlined is xy, it's in 2 dimensions. And here is the function h, right? And there's and what we're trying to do is to find the place in xy that corresponds to that locus. Well, you understand that a ridge, intuitively, if you walk across the ridge, you're going up and over, right? If I walk in this direction here, across the ridge here, you'll be going up and over. It's a kind of a maximum, relative max, but it's a subdimensional max. It's not your normal max of a function h of x, xy, is a relative max in 2 orthogonal directions. Okay, you go up and over. I mean, so if you have a hilltop, then if you go in this way, you have a max. And if you go in an orthogonal direction, you also have a max. Which is to say, both 2 different orthogonal first derivatives have to be 0, right? And that's another way of saying the gradient of h is equal to 0, because gradient is, of course, first derivative in one direction, first derivative in an orthogonal direction. But we're not going to be interested in relative max in 2 dimensions. We're only interested in a relative max in 1 direction. And that begs the question, which direction? Okay? What we're trying to do is to find a place where the first derivative in some v direction of h is 0, but the question is, what v? Okay? Okay. We will see that if the ambient space is capital F, of dimension capital M, which in this example is 2, and the dimension of the ridge, here's a curve, is 1, then we're going to need big M minus little m first derivatives to be 0. Right? And since 2 minus 1 is 1, we're going to be having a single, in this example, first derivative equals 0. But to be a relative max, it's not enough that this equals 0, because that could be a relative min as well. And so to be a relative max, we're going to need that the second derivative twice in that direction is less than 0, meaning the function is convex downward. Right? So we need first derivative v equal to 0, and at that place, that's a ridge, the function has to be convex downward, which means the second derivative in that, twice in that direction, is negative. Okay? Okay, so then the most, a very common, particularly common choice for V is the direction where the curvature is sharpest, right? So if I cross the ridge sort of this way, it won't be as sharp as if I cross the ridge that way, across the ridge. Okay, so, and that's to say that the second derivative, which is negative, is as negative as it possibly can over all V's. And we have seen that the direction for which that minimum of a negative minimum, because it's the greatest magnitude negative value, at which that is the direction of the eigenvector of the Hessian of H. So we look at the Hessian of H, right? It's a 2x2 matrix. It's a 2x2 symmetric matrix. It has two orthogonal eigenvectors, two associated eigenvalues. One of them, if at least one of them is negative, you have the possibility of having a relative max, right? And the one with the most negative, if they're both negative, the one that's more negative has an associated eigenvector, and that's V. That's the maximum convexity direction, so-called. Okay? And so to find the ridge, you, at any given point, you are looking at this 2x2 matrix at that point, right? This is D2H at X. And at any point, we can look at this place, this eigenvector, and its eigenvalue. Sorry, we look at the eigenvalues. If neither one is negative, we know there's not a ridge there at all, right? And if one of them is negative, we will then compute the first derivative in that eigenvector direction. And if it's 0, then we are at a ridge point, and if it's not 0, we're not at a ridge point. Okay? Strictly speaking, what we will find is, because we're in pixels, there may be a pixel where it's a very small positive value, the next door pixel, small negative value, and the ridge goes between them at the 0 crossing between those two places. Okay. We'll be talking about a common derivative, a common edge algorithm due to John Canny, called the Canny Edge. And then we'll see that instead of using the maximum convexity choice for V, that there's another possibility, well, the one that Canny chose for V, okay? And it turns out it's the maximum edge strength direction. Okay, so these are Canny edges for an image here, and you'll see that you have dark bars on a lighter background, dark code on a lighter background, but also a light piece of the camera on a darker background, and they all produce Canny edges, bridges. Okay, so how does the algorithm work for finding a ridge? Well, the answer is, first of all, find some place where boy, I changed this and then I brought up the wrong thing. It should be. Okay, so the basic idea is you find some place where things are convex downward, where the most negative eigen, I think the version I have up on is that correction on. Anyway, the point is that you find some place or another where the second derivative is negative in the most negative, the second one of the eigenvalues is negative. And from that place, you can march uphill. March uphill means march in the direction of gradient of h. Right? And we keep, at that point, we will compute we'll take a little step, and we will then recalculate the eigenvector direction, the eigenvalue there, and make sure it's negative. And if so, we'll move further uphill, and eventually we'll move uphill to the ridge. Okay. Strictly, we don't march in the gradient of h direction, because when we get near the ridge, we're going to turn away from the ridge because it becomes 0. What we're going to march up instead is in the eigenvector direction v. Okay? So we're going to go, if you will, uphill in that direction that had the most negative eigenvalue. And you keep, as you look at that, you look at the first directional derivative in that direction, which is v dot grad of h, called j here. Sorry. Somebody had, as I said, I fixed that. Okay, once we're there, we have found a point on the ridge, and then we can look at the direction orthogonal to v and take a little step in that direction. So we've found a ridge corresponding to this direction. We look a little bit in that direction. We take and that'll let us more or less follow the ridge, but fall off it. And then we can climb back up using this algorithm. right? Find the second derivative, the Hessian there, find its eigenvector corresponding to the most negative eigenvalue, go uphill on that, in that direction until we get back to the ridge. Now we get a new ridge point. We will go orthogonal direction as well. Notice that the ridge doesn't have to be straight. In this example, my ridge is a curve in the plane, right? Questions about that way of operating? Okay. Only difference from Canny Edge is that we don't choose V as the eigenvector associated with the most negative eigenvalue. We choose V as something else. And in the Canny Edge, we use the gradient direction for V. Okay? So X is a ridge point, a Canny ridge point, if your relative maximum in the first derivative in the gradient direction, this is the gradient divided by the gradient magnitude, which is the gradient direction of the gradient magnitude. Don't get confused. You're taking the derivative of the gradient magnitude in the direction of the directional derivative of the gradient direction. Okay. But other than that, you don't have, this is not a so-called maximum convexity ridge, but the Canny ridge, it's a perfectly intuitive ridge. It's not the same as the maximum convexity ridge. It's a slightly different curve, but that's the one that Canny suggested. Okay? So far, so good. We've now talked about ridges of gradient magnitude in 2 dimensions. We're talking about 1-dimensional ridges. Now let's talk about functions of 3 variables. Okay, so now your image is a 3-dimensional image. Your gradient magnitude is a scalar value at any point. It's the first derivative in x of the image squared plus the first derivative in y squared plus the first derivative in z squared, all to the half power. Okay, fine. We're big M equals 3. Now we're interested in the surface of, so I'm going to take my hand as an example. I have, let's say, high density inside my hand and low density outside my hand. And I'm looking for this surface, and the surface is 2-dimensional, right? At any given point on my hand, there's a plane, which is tangent, that's 2-dimensional. Big M equals 3, little m equals 2. We're going to be interested in a 2-dimensional ridge in a function of three dimensions. Big M minus little m in this example is again 1, 3 minus 2. Okay? Well, now we're going to still find a direction, one direction, because this constraint lowers the dimension by 1. So you're in 3 dimensions. When you have a constraint, it lowers it from 3 to 2. In our other example, it lowered the dimension from 2 to 1. Constraints take away a dimension. Every constraint takes away a dimension. So we have 1 dimension to get down from 3 dimensions to our 2-dimensional surface that we're wanting. So we're going to need a single V for which the first derivative is 0, and the second derivative is less than 0. Okay? So, play the same game. Now our Hessian is 3 by 3, symmetric. It's going to have 3 eigenvalues. At any given point, the Hessian of H is going to possibly have 3 positive eigenvalues, in which case it's not a ridge point. Or if it has a negative one, take the most negative one, take the eigenvector in that direction, that's the maximum convexity choice. And we play the same game, and that is to say, in that direction, we want to find, if you have this condition already said, you want to find whether the first derivative in that direction is 0. And then you have this relative max property. Now, a direction across from the inside of my hand to the outside of my hand. And if I walk in that direction, I have a maximum of, in this case, the gradient magnitude to be my ridge. Okay? Still good? Okay. There's a corresponding Canny Canny choice. Okay. I guess what I did was I fixed it in my other computer and not here. Okay. So now let's consider big M equals 3. But my choice here is going to be a scale space. Right? So H is going to be a function of X and Y and sigma. Right? So my original image is 2-dimensional, but once I convolve it with Gaussians of various sigmas, I will get H as a function of 3 dimensions, X, Y, sigma. And I'm interested in a curve in scale space, right? X, Y on the table, scale going up. A curve that is going to be a locus that is going to correspond to my edge, or my ridge. Now big M is 3, X, Y, sigma. Little m is 1. So we're going to need 2 constraints to get down to 1 dimension from 3. So we're going to need two requirements for B. Two constraints in 2 orthogonal directions. So we're going to need a V1 and a V2, 2 directions at any point in XY sigma. We'll do that by looking at the eigen analysis of this 3 by 3 Hessian. And it will need 2 negative eigenvalues. And the corresponding eigenvectors. If there are 3, it's the 2 most negative of them. The corresponding eigenvalues will be respectively V1 and V2. And then we're in Fat City. We have a pair of directions that we can test for where the first derivative is equal to 0. Notice that only in those two directions that it need to be 0. There's a third eigenvector, and that one need not be 0. Just to make the point here, for this big M equals 2, little m equals 1, this ridge can be up and over in this direction, but you could be going down and up in the orthogonal direction, right? So when you're walking along a ridge, you're not necessarily at a relative max, because when you walk along the ridge, you could be going uphill, or you're walking along the ridge, you can be going downhill, right? Just still staying on the ridge. Okay, so there's another choice that people make, also valid, so-called optimal scale ridge, where you choose one of the directions to be the pure sigma direction, the unit direction in sigma, and the other is, for example, a maximum convexity direction with the more negative eigenvalue. Oh, what happened here? We lost Millie. So Millie, I am sorry. I don't know how you disappeared from this, and I only saw that you needed to be admitted. You'll have to look at the recording. Okay, so the Canny Edge is one of these optimal parameter ridges. But anyway, it all has to do with taking some of the directions as the largest of some criterion. The maximum convexity choice is the direction you choose is the optimum, most negative of eigenvalues, or second derivative, the lowest, most negative second derivative direction. Okay. Barness. Right? So now we have a bar. An image. And we're thinking of it as a function h. That's a function of x and y, and the width of the bar and a direction across the bar. Right, so this h now is going to be a function at any given position of in which direction goes across the bar and of how wide the bar is. We're in two dimensions, so u is just an angle. It's a single parameter. So now we have big M equals 4, right? X, Y, W, theta. And what we're trying to do is to find a curve that runs down the center of the bar. That corresponds to something that's W wide, and the angle and orthogonal to that curve is this, the width W is how wide the bar is. So now big M equals 4, little m equals, on here, just read it. 1, it's a curve you're trying to find, in 4 dimensions. So you're trying to find a one-dimensional ridge in 4 dimensions. You need 3 constraints. So you can play the same game all over again. Add another constraint. D1, V3 of H equals 0. D2 of V3, V3, V3 of H should be less than 0. So we're going to look at the Hessian in 4 dimensions. It's going to be a 4 by 4 matrix for edgeness, barness, bar strength. We're going to take the line places where 3 of the eigenvalues are negative. The 3 most negative ones are going to give you 3 directions, V1, V2, V3, and you're going to need relative maxes in all 3 of those directions. D1, the first derivative is 0 in V1 direction, in V2 direction, and in V3 direction. Clear how it goes? You need as many constraints as to get the ambient space, in this case 4 dimensions, down to the desired dimension. In this case, a curve, 1 dimension, so we need 3 directions. All right. Well, at this point, we can talk about this generally. Right? You have a big M, you have a little m, you have a function of a scalar function of big M variables, and you need big M minus little m constraints. If you use the maximum convexity criterion, you're going to have that many eigenvalues of the Hessian, the big M by big M Hessian, to be negative. You take the ones with the big M minus little m ones that are most negative, you choose the corresponding eigenvectors, and you take first derivatives in each one of those, and you want each one of those you want to have a 0 value of the first derivative. Okay? I swear, this one is. This was from last year's. The one online is not this slide, which is basically saying what I just said. You need to figure out what big M is, what little m is. You need that many constraints, and you need that many eigenvalues to be negative. Okay. This is fine, but there's something that's a little bit concerning. The algorithm that I have told you about for finding ridges basically involves finding your way up to the ridge and then moving in however many dimensions you have along that ridge and climbing back up and so on. But unfortunately, height ridges end. And we need to understand why they end. And the answer is it is not the case that there stops being directions in which the in which h has an extremum. But what can happen is the ridge can get less and less and less sharply curved. So as you walk along the ridge, going across the ridge, as you walk along, it is sharp here, and then it gets less sharp, and then it gets less sharp, and so on, until at some point it flattens out in the cross section. The second derivative becomes 0, and then the second derivative becomes positive. The second derivative can cross 0 from being negative to being positive as you walk along this locus. And that's why the ridge ends, because the second derivative changes sign. And it becomes some kind of a saddle rather than a ridge, actually. And then if you walk along further, you can still walk along that curve, but you'll have one of the eigenvalues no longer negative that needed to be. And then eventually it may be that it flattens out again as you walk along the ridge and eventually becomes appropriately convex downward. And so you can pick up again the ridge if you keep walking along it. So the point is the ridge, so you get a curve that over here is no longer a ridge, but it's still first derivative equals 0, and then it picks up again as ridge. What can cause that? Well, noise in the image, boulders on your, or I'm going to call it, and a better example is little holes as you're walking along the ridge. There's a depression along the Blue Ridge. And in that depression, there's no longer a ridge, but you can still walk the curve. Yeah.
The depression would be sort of, maybe not necessarily in a thought of a direction, but somewhat of an about of a direction.
Well,
You think it's still go down.
yeah,
Yeah.
exactly. Exactly. Okay, so you have these sort of connector curves where the first derivative is still 0, but you don't satisfy the second derivative criterion or criteria. And in higher dimensions, you can even get worse. So if you have 3 criteria, you can lose one of them, and then you keep walking along, and then you lose the second one, and then maybe you pick up the second one again, and then maybe you pick up the third one again, and then you're back on a ridge. Okay. Here's an interesting question. What's the dimension of the ridge when big M and little m are the same? 0. Big M, little minus little m. What's a 0-dimensional entity? It's a point. How many constraints are you going to need to get from big M directions down to 0 dimensions? Big M or little m, they're the same, right? So for example, a function of 3 dimensions, you need 3 eigenvectors values of your Hessian all to be negative, and you need to be a first derivative in all three dimensions be 0. What is that called? A point where in three orthogonal directions in 3 space, function of 3 variables, you have 0 first derivative.
Critical point?
Hmm?
Well, it could be any kind of critical point.
It's a critical point. That's right. It's a with these constraints of negative first derivatives, it's a relative max. So a relative max is a kind of ridge. It's just a 0-dimensional ridge, right? These are, in general, subdimensional maxima. But for the particular case where it's in all dimensions, then you have a relative max, and that's just a 0-dimensional ridge. Okay. So I've finished my discussion of height ridges, and that's what you're responsible for. Okay? But there are other kinds of ridges, and one in particular that's quite important. And it's used frequently, partially because it's very easy to compute, very fast to compute relative to these height ridge properties. And it turns out that you want to take these derivatives typically at multiple scales, and it's very easy to use a multi-scale analysis. And that's the so-called Watershed Ridge. Okay, so let's first of all understand what a watershed is. We have an eastern watershed in the Watershed Ridge in the Blue Ridge. On one side of it, if you drop water, it goes down and it runs into the Atlantic Ocean. On the other side, water runs down and it goes into the Mississippi and gets to the Gulf of Mexico, right? There are sort of two catchment basins. One, the lowest place in the Gulf of Mexico, another, the lowest place in the Atlantic off our east coast. And the ridge is the place, the Watershed Ridge is the place that separates where this water runs down into one and the other. We have another ridge in the Rockies somewhere where water runs down to the Pacific on one side of it and to the general Atlantic, the Atlantic plus the Gulf of Mexico on the other side, right? It has to do with where water runs down. One of the properties of the Watershed Ridge, unlike the height ridge, is that it's a non-local property. If you're on a place X, Y, and you have the height, you know by these tests that I've just talked about whether you're on a height ridge or not, just from the derivatives at that point. But let's put in a big, enormous high dam in the Colorado River, in such a way that when the water runs off the Rockies, it comes to this dam in Arizona somewhere, and the water is directed back west to Texas, and back east to Texas and into the Atlantic. I've put a dam in Arizona, and a place in Colorado has changed whether it's on the Watershed Ridge or not. It's a non-local property, and that's not particularly desirable, but nevertheless, it's a nice thing to be able to calculate, because literally you can put drops of water everywhere and follow them downhill along their gradients and see which pit they end up at. And then you classify this as the water runs into pit 1 from here or pit 2. And despite the non-locality, you can get some fairly nice ridge locations using the idea that when you run downhill, you run to some pit over here. When you run on the other side, you run to some pit that's between these two edges. And when you run down from this side, you have a third pit. And so you divide the place into relative minima of the height function, and then you figure out where all the trails going downhill are. I'll note that if this height function has a little ridgelet on it, the height ridge property will still pick out these places. But the water will run downhill past these without differentiating what pit you're in. And so it's certainly not the case that the watershed ridges and the height ridges are the same place. They're not even the same place for the main ridge. They're typically close, intuitively, but not exactly the same. But you will find in image computing a lot of use of the watershed ridge. And the problem is that when you take an image and you look at all the watershed ridge, if you have a somewhat noisy image, you get a zillion pits. And every single one of these places in this curve ends up being a watershed ridge. And then you're in trouble because you're trying to use this to find regions like we see here. This is a cut through the head in a CT image where the red region is the region of the brain and the yellow is the region of the skull, and then you're outside the head. And so you're really trying to find the red to yellow watershed ridge and the yellow to blue watershed ridge. And how the heck do you get that from here? Multi-scale is the answer. You start taking Gaussian convolutions for larger and larger sigma. And as sigma increases, what happens is that some of these watershed ridges join by flooding. And you get a single pit instead of the two. And so you break up two of them into the union of the two. And then you take a bigger sigma yet, and you get more coalescence. And eventually, if you, at some sigma, you end up with just what you want. Okay, and there are algorithms for a person, interactive person, to point. There's a point, a red point, a yellow point, and a blue point. And then you let this multi-scale thing come until those three are separated. You'll see this referenced by Olsen and Mess Nielsen, who are at the University of Copenhagen. For those of you who like to pronounce names right, or at least in their original, realize that there are only two Western languages that I know of that has the sound ah. Ours and Danish. And all the rest of the Western languages have ah. Not just Western, lots of Eastern languages have ah and not ah. right? And so if you're trying to pronounce somebody by some European's name and they're not Danish, you shouldn't call them, you know, Ram, you should call them Ram. Okay? Anyway, this pronunciation guide suggested because these two guys are Danish. This is the end of my lecture on ridges. Let me summarize. There are multiple definitions of ridge. The two most commonly used are the height ridge and the watershed ridge. They're not the same. The watershed ridge is typically more quickly calculated, but it requires this multi-scale approach. And the height ridge also benefits from being in scale space, but you have to compute a bunch of second derivatives and a bunch of first derivatives and so on. And you can talk about an ambient space of big M, which may be just the original intensity, the original spatial variables, but maybe, as in our example here, maybe dimensions other than positional, like width of a bar or the direction of a bar. And big M, little m, you figure out the dimension of the ridge you want, you work out, you want big M minus little m constraints, each of which is of this form. And then you can find places that are on that height ridge. End of ridge lecture. Okay. I have 2 minutes, and I'm going to say there's a very, very quick thing that it's worth knowing about. That will be at the end of the course material. One way to understand an image, the way we normally do, is as a pile of, an array of pixels in 2 dimensions or voxels in 3 dimensions and so on. And when we have that arrangement, we have for every pixel a bunch of neighbors, right? In 2 dimensions might be the horizontal and vertical neighbors, or you may choose to use the diagonal neighbors as well. And then you can have this notion of neighbor affinity, how like your neighbor you are. Okay, so the basic idea is what's called an algebraic graph. Every pixel, or in 3D voxel, is a node in the graph. And you have these other pixels, and you have arcs going between the nodes. And the arcs are labeled by the affinity of one pixel with the next. And the general idea for edges is that the places inside have good affinity with their neighbors and bad affinity with their. And so this graph that you have, this guy has neighbors here and here and here and here, and so on. The notion is that you want a locus of low affinity connections surrounding regions of high infinity. This thing of nodes and edges is called an algebraic graph, not to be confused with the analytic graph, which is a function like like this, right? That's a f of x. And this algebraic graph, you end up wanting to find a cut in this graph, through this graph that separates it between the object and the other part, the background. And so you end up, turns out in the algorithm, having a source node and a sink node, sink, like that kind of sink. And you end up trying to get everything from the source that has a hard way through and everything else flows into the sink. And that turns out to be an interesting algorithm for segmentation that's called graph cuts. This is yet another way of finding edges. The problem with using the ridge is the following the ridge part. It's easy to find the ridge. It's hard to follow the ridge because of the boulders and the pits on the ridge. And the graph cuts alternatives turns out to be a useful way of producing with an interesting algorithmic solution that is not part of this course. Okay, so this was graph cuts. Okay, we're done. We're done with the material in the course. Summary next time with questions from you and more questions in the final lecture.